Welcome back to QHSE Talks.
Yeah.
Today we have a really intense scenario to kick things off.
Yeah, it's a good one.
Right. So I want you to imagine you are walking the floor of this massive, temperature-controlled warehouse. It's the midnight shift.
Nice and quiet.
Exactly. The facility is practically silent. And over in, let's say, aisle 4, there is a perfectly normal, sealed plastic pallet of newly manufactured synthetic foam.
Just sitting there?
Just sitting there.
Yeah.
There are no exposed electrical wires anywhere near it. No sparks, no hot machinery, definitely no careless worker smoking a cigarette or anything like that.
Right.
The ambient temperature in the building is a very comfortable, 68 degrees.
Which feels totally safe.
Totally safe, right?
Yeah.
Yet, somewhere deep inside the center of that tightly wrapped pallet, the temperature is quietly climbing past 400 degrees.
Yeah, that's where the physics take over.
Right. The synthetic foam is slowly oxidizing. It's, feeding on itself, trapped within its own thermal insulation. And then by 2:00 a.m., without a single external ignition source, that pallet spontaneously bursts into flames.
And that sets off a chain reaction that could, easily level the entire facility.
It's wild. So our mission today on QHSE Talks is highly specific, incredibly technical, and absolutely critical for any safety professional, especially if you are currently staring down Domain 4, Topic 2 of the ASP exam.
Oh, yeah. That's a huge one.
It really is. We are systematically tearing apart the science of flammable and combustible materials today.
Which is so much more than just memorizing definitions.
Exactly. We're going to look at their chemical properties, their physical behaviors, the really strict rules for handling them, and, the complex web of chemical compatibility.
Because, this isn't just about passing a test, right?
No, not at all. This is the fundamental bedrock of keeping your worksite from becoming a crater.
Yeah, and the scenario you just described with the synthetic foam is, it's the perfect anchor for this discussion.
You think so?
Oh, absolutely. Because it shatters the illusion that fire is always an accident, caused by human error or a rogue spark.
Right. We always picture a guy dropping a blowtorch or something.
Exactly. But fire is simply a rapid chemical reaction. If you put the right ingredients in the right physical state, the laws of thermodynamics take over, and, combustion becomes inevitable.
It's just math at that point.
It really is. So when we talk about ASP exam domain 4, we have to move past rote memorization.
Right, because you can memorize flashpoint tables and hazard classifications until your eyes blur.
Yeah, but if you don't understand the kinetic molecular behavior driving those numbers, the why and the how, you cannot effectively design a safety program.
It's just blind compliance otherwise.
Exactly. We have to look at how these chemicals behave at a microscopic level under, real-world stress to understand why OSHA and the NFPA wrote the regulations the way they did.
Right. We have to understand the invisible mechanics before we can control the physical hazards.
Yeah.
And I guess that brings us to the most fundamental dividing line in the entire field of fire science, right?
The big one.
Yeah, the classification between flammable liquids and combustible liquids.
Which, to the general public, are basically synonyms.
Totally. If something is flammable, it burns. If it's combustible, it burns, right?
Right. But in the realm of safety engineering, mixing up those two terms can literally be a fatal error.
Wow. Okay, so the entire regulatory framework hinges on one specific, highly tested metric, right? And that is the flash point.
Yes, the almighty flash point.
Let's unpack the formal definition first and then, translate it into reality. Because the books say the flash point is the minimum temperature at which a liquid gives off sufficient vapor within a test vessel to form an ignitable mixture with the air near its surface.
Right, and breaking that definition down to its physical reality is crucial here.
Okay, where do we start?
Well, notice that the definition specifically focuses on the vapor, not the liquid. Oh, right.
Liquids themselves do not burn.
Wait, really? Because I feel like if I throw a match in a puddle of gas, the puddle is on fire.
It looks that way, but no. That is a cornerstone concept that is frequently misunderstood, even by, seasoned professionals.
Mm-hmm.
The liquid state is too dense. Too dense. Yeah, the molecules are too closely packed together to allow oxygen to intercalate and react rapidly enough to actually sustain a flame.
Okay, so what is actually burning then?
What actually burns is the gas phase. It's the vapor that has broken free from the surface tension of the liquid and mixed with the oxygen in the ambient air.
Okay, I find it helpful to visualize a flash point as a chemicals, like sweat point.
I like that. Sweat point.
Yeah. Imagine you are outside on a hot day, right? Your body reaches a certain temperature and you start giving off moisture to regulate heat.
Right.
A liquid does something conceptually similar, though, governed by kinetic energy. Every liquid has molecules bouncing around inside it.
Constantly moving. Exactly. As the temperature rises, that thermal energy increases the kinetic energy of the molecules.
They get agitated.
Yeah, and at a very specific temperature threshold, the flash point, enough molecules have the kinetic energy to overcome the intermolecular forces holding them in the liquid state.
And they break free?
Right. They basically sweat out into the air above the surface as an invisible vapor.
And this kinetic activity is constantly happening, trying to reach an equilibrium.
Okay.
The flash point simply marks the exact thermal threshold where the concentration of those escaped vapor molecules becomes dense enough that a single spark can initiate a chain reaction.
Okay, that makes sense.
Yeah.
So this brings us to how OSHA actually draws the regulatory line.
Right, the 100-degree mark.
Yeah, flammable liquids are defined as having a flash point below 100 degrees Fahrenheit, which is 37.8 degrees Celsius for those keeping track.
Yeah.
They also must have a vapor pressure not exceeding 40 pZ at that 100-degree mark. We'll get to the vapor pressure in a second, but we really need to pause on that 100-degree Fahrenheit threshold.
It's super important.
Why is the line drawn at 100 degrees? Because it isn't just, an arbitrary number pulled out of a hat.
No, it's very deliberate.
Right. When you look at the global climate in typical industrial environments, 100 degrees represents a standard maximum ambient temperature.
Right. It represents a hot summer afternoon in a warehouse without air conditioning.
Exactly.
And the regulatory logic there is just brilliant in its simplicity. If a liquid has a flash point below 100 degrees Fahrenheit, it means that the ambient environment itself, just the normal weather or the standard temperature of a manufacturing floor, provides enough thermal energy to make that liquid continuously emit an ignitable cloud of vapor.
Just by existing in the room.
Exactly. You don't have to put it on a stove. You don't have to introduce it to a chemical process.
Wow.
Just by sitting in an open bucket on a July afternoon, a flammable liquid is actively pushing a dangerous volume of fuel into the breathing zone of your workers.
That's terrifying. What's a good example of that?
Well, gasoline is the classic example. Its flash point is around negative 45 degrees Fahrenheit.
Negative 40.
Yeah. So even in the dead of winter in Alaska, gasoline is absorbing enough heat from the freezing air to generate explosive vapors.
That is wild. So flammable liquids are the ones constantly sweating vapor without any help.
Right.
Okay, so then combustible liquids are defined as having a flash point at or above 100 degrees Fahrenheit, specifically categorized up to 200 degrees Fahrenheit or 93.3 Celsius.
Correct.
Because their flash point is so much higher, combustible liquids are inherently more stable at normal room temperature.
Right. Much more stable. Diesel fuel is the perfect counterpart to our gasoline example.
Okay, how so?
Well, the flash point of typical diesel fuel ranges from 125 to 140 degrees Fahrenheit.
So well above room temperature.
Exactly. If you have a spill of diesel fuel on a concrete floor in a facility that is kept at 68 degrees, the kinetic energy of those diesel molecules is too low to break surface tension in significant numbers.
So they aren't sweating.
Right.
Yeah.
If you were to drop a match onto that 68-degree puddle, the match would very likely extinguish itself when it hit the liquid.
Really? Just go out.
Yeah, because the environment is simply too cold to coax enough vapor out of the diesel to support combustion.
Okay, but the danger of combustible liquids is that their stability is entirely conditional, isn't it?
Yes, highly conditional.
Because if you take that exact same puddle of diesel fuel, and let's say a nearby piece of machinery catches fire, radiating heat across the room,
Right.
the temperature of that diesel puddle will start to climb.
And once it crosses 125 degrees Fahrenheit, it abruptly transitions from a stable puddle into a massive fuel source.
Behaving identically to a flammable liquid.
Exactly. And the conditional nature of combustible liquids is what catches facilities off guard all the time.
Because they get complacent.
Precisely. Safety protocols often treat combustibles with a relaxed attitude because they don't pose an ambient threat.
Oh, I see.
But in the event of an adjacent thermal event, a steam pipe rupture, a localized electrical fire, or even being pumped through a high-friction mechanical system, combustibles require the exact same suppression strategies as flammables.
That is a huge takeaway for the exam. Okay, I want to circle back to the second half of the flammable liquid definition because it introduces a highly technical engineering concept.
The vapor pressure.
Yeah, the regulation states a flammable liquid must have a vapor pressure not exceeding 40 psi at 100 degrees Fahrenheit.
Right.
For the safety practitioner out there trying to understand the physics of their materials, what exactly is vapor pressure, and why is 40 PSI the magic cutoff?
So vapor pressure is basically a measurement of the mechanical force that the evaporating gas exerts against the atmosphere trying to keep it contained.
Okay, so it's pushing back.
Exactly. If you put a liquid in a completely sealed, vacuum-evacuated container, some of the liquid will turn into gas.
Natural.
And that gas pushes outward against the walls of the container. The pressure it generates once the evaporation and condensation rates stabilize is its equilibrium vapor pressure.
Okay, I'm following.
Now, atmospheric pressure at sea level is roughly 14.7 PSI.
Right.
If a chemical's vapor pressure exceeds atmospheric pressure, the liquid boils.
Oh, so the vapor pressure is basically the chemical's desire to become a gas, fighting against the weight of the Earth's atmosphere pushing down on it.
That is a highly accurate way to frame it.
Okay, so why 40 PSI?
OSHA sets the boundary at 40 PSI at 100 degrees Fahrenheit because 40 PSI is almost 3 times normal atmospheric pressure.
Wow, that's a lot of push.
It is. If a chemical is pushing outward with 40 pounds of force per square inch at just 100 degrees, it has completely overwhelmed the 14.7 PSI of the atmosphere.
It won't stay in a liquid state in an open container under any normal earthly conditions.
Never. At that point, it is no longer governed by the rules of flammable liquids. It is legally and physically classified as a gas.
Which triggers an entirely different set of storage and handling regulations.
Exactly, involving pressure vessels, sterilized valves, all of that.
This just highlights the elegance of the regulations, honestly. The 100-degree flash point separates ambient threats from conditional threats, and the 40 PSI of vapor pressure separates liquids from gases.
It's a very clean system.
It really is. Okay, so once we have established that a liquid is actively releasing vapor, let's say a highly volatile, flammable solvent leaking from a drum,
Okay.
the immediate hazard assessment question shifts. We know the vapor is forming, but where is it going?
That is the million-dollar question.
Right. We have to track the invisible threat, which brings us to the physical properties of vapor density, specific gravity, and solubility.
And understanding how these chemicals migrate through physical space is the absolute essence of emergency planning.
So vapor density is the starting point.
Yes. It is a comparative ratio. The density of a specific chemical vapor compared to the density of ambient air.
And air is the baseline.
Right? Air is assigned a baseline value of 1. If a chemical has a vapor density greater than 1, it is heavier than air and will sink.
Okay.
If the vapor density is less than 1, it is lighter than air and will rise and dissipate.
You know, if you're walking the floor of a chemical processing plant, vapor density is the metric that should keep you awake at night.
Absolutely.
Because our brains are hardwired to associate gases with smoke or steam, both of which rise.
It's an instinct.
Yeah, but most flammable solvents used in industry have a vapor density significantly higher than 1.
Toluene, hexene, xylene.
Yeah, these vapors are incredibly heavy. Imagine an invisible river of heavy, highly flammable gas silently pouring out of a leaking tank.
Just flowing right out.
Because it's denser than air, it doesn't float away. It flows like water. It cascades off the edge of a workbench, flows across the factory floor, pours down the stairwells, and begins pooling in basement trenches, sewer lines, or elevator shafts.
The phenomenon you were describing is called gas stratification, and it is a massive engineering challenge.
I can imagine.
The vapors seek the lowest possible topological point and displace the oxygen in those confined areas.
So a worker could be in danger far away from this goal.
Exactly. A worker might enter a sump pit or a basement utility trench 3 buildings away from the actual chemical leak.
And they can't see the vapor.
They can't see it. They may not even smell it due to olfactory fatigue.
But that trench is filled with an explosive atmosphere.
And when they turn on a non-intrinsically safe flashlight or, drop a steel wrench on the concrete, they trigger a catastrophic detonation far removed from the source of the spill.
Which completely upends how we design ventilation systems.
It has to.
If you don't factor in vapor density, you might build a perfectly compliant-looking storage room that is actually a death trap.
Yeah, designing ventilation without accounting for vapor density is architectural negligence.
Wow.
Standard commercial ventilation relies on ceiling exhaust fans, drawing warm air up and out.
Right, heat rises.
But if you place a heavy, flammable solvent in a room with only ceiling ventilation, the exhaust fans are just moving clean air around the top of the room while the hazardous vapor concentrates on the floor.
They aren't doing anything to the actual hazard.
Nothing. For high vapor density materials, you must engineer floor-level exhaust systems. The ductwork must literally sweep the heavy gas off the ground, often requiring makeup air to be supplied from the ceiling to create a laminar downward flow that pushes the heavy vapors into the exhaust intakes.
So the ventilation must match the kinetic behavior of the hazard. That makes total sense.
Exactly.
So vapor density tells us where the invisible gas goes. But what happens if the spill is liquid and we introduce water into the equation?
Now we get to specific gravity.
Right. That operates on the same mathematical principle as vapor density, but for liquids instead of gases. Specific gravity is the ratio of a liquid's density compared to the density of water, with water serving as the baseline of 1.
And this ratio dictates the entire tactical approach of emergency responders.
Okay, how so?
If a chemical has a specific gravity less than 1, it is lighter than water and will float on the surface. If it is greater than 1, it is denser than water and will sink.
Simple enough.
But you have to combine specific gravity with the concept of solubility.
Which is the chemical's ability to dissolve into a solvent.
Right, which in industrial emergencies is almost always the water being pumped from a fire engine.
Okay, let's put you, the listener, in the boots of an incident commander.
Good exercise.
You arrive at a facility, and there is a massive pool of burning liquid. The instinct is to pull the hoses and flood the area with thousands of gallons of water.
Put the wet stuff on the red stuff.
Right. But if that chemical has a specific gravity less than 1, and it is insoluble, meaning it refuses to mix with water, the physics of the situation turn the water into an accelerant.
The mechanics of that interaction are just devastating.
Because the water goes right under it.
Yes. Water is heavier than the burning fuel, so as the water streams into the puddle, it sinks rapidly to the bottom.
And the chemical?
The burning chemical simply floats on top of the growing layer of water. You are not cooling the chemical. You are not separating the fuel from the oxygen.
Oh, man.
You are physically lifting the burning liquid up and giving it a frictionless vehicle to travel on. The water flows down the floor drains, out the loading dock doors, and into the municipal storm sewers, carrying the burning chemical across the entire property.
You've essentially weaponized the fire.
Yes.
Spreading a blazing slick of oil everywhere the water flows. Not to mention, if the burning oil is hot enough, the water sinking beneath it can rapidly boil, right?
Oh, absolutely.
And when water boils, it expands to, 1,700 times its volume as steam?
Yep. And it violently ejects the burning oil into the air in a massive boil-over event. The slop-over or boil-over phenomenon is exactly why specific gravity must be known instantly by responders.
You don't have time to look it up while the hose is running.
Exactly. For a lighter-than-water, insoluble liquid, firefighters must switch tactics and deploy specialized firefighting foam.
Right.
The foam is designed to be lighter than the fuel floating on top of the burning liquid.
Okay, so it sits on top.
Yeah, it creates a physical barrier that cuts off the oxygen and suppresses the release of those flammable vapors we discussed earlier.
But solubility adds a nasty twist to the foam strategy, doesn't it?
Yeah, it sure does.
Because if the burning chemical is a polar solvent, like an alcohol or a ketone, it might be highly soluble in water.
And the molecular polarity changes the entire game.
How does the foam react to that?
Well, standard firefighting foam relies on water suspended in a bubble structure.
Right.
If you spray standard foam onto a highly water-soluble chemical like ethanol, the chemical's affinity for water is so strong that it literally pulls the water out of the foam bubbles.
Wait, really? It just drinks the foam?
It basically does. The foam blanket dissolves and collapses on contact, rendering it completely useless.
That's incredible.
In those scenarios, you must use an alcohol-resistant aqueous film-forming foam, or ARAFF.
The special stuff.
Right. It contains special polymers that precipitate out and form a physical membrane between the chemical and the foam to prevent the solvent from eating the water.
Man, it is a phenomenal chess match of chemistry.
Every single decision matters.
Yeah. Vapor density dictates your ventilation and gas detection placement. Specific gravity dictates whether you can use water or if it will just spread the disaster. Solubility dictates whether your foam will smother the fire or instantly dissolve.
Every property has a tactical consequence.
Exactly. Every single decision requires a granular understanding of the material's physical properties.
Yeah.
But let's assume the worst has happened. We have an invisible, heavy vapor pooling in a trench. We know the fuel is present. We know the oxygen is present in the air.
All the ingredients are there.
The final piece of the puzzle is the ignition itself, which brings us to the mechanics of flammable ranges and autoignition.
Right. The initiation of a fire requires a very precise stoichiometric ratio of fuel to oxygen.
A ratio.
Yes. We call this the flammable range or the explosive range. It is the specific concentration band of a vapor-air mixture that will successfully support a self-sustaining combustion reaction.
And there are limits to this band.
Correct. This band is bordered by the lower flammable limit, the LFL, and the upper flammable limit, the UFL.
Though you will frequently see these referred to on the exam as the LEL and UEL, standing for lower and upper explosive limits.
Interchangeable terms, basically.
Right. So to understand the lower limit, the LFL, we can look at the thermodynamics of the reaction. Below the LFL, the mixture is considered too lean to burn.
Too lean.
Yeah. There's plenty of oxygen, but the vaporized fuel molecules are too sparse, too spread out.
Right, they can't connect.
Exactly. If you introduce a spark, you might get a microscopic localized reaction right at the spark site, but the heat generated isn't enough to reach the next distant fuel molecule.
The reaction simply starves and dies because the chain cannot sustain itself.
Because the thermal energy just dissipates.
Exactly. It dissipates into the surrounding inert air faster than the chemical reaction can generate it.
Okay, that makes sense.
Now, as the concentration of fuel vapor increases, you cross the threshold of the lower flammable limit and enter the flammable range.
The danger zone.
The danger zone, where the spacing between the fuel molecules and the oxygen molecules is optimal for a rapid, self-sustaining chain reaction.
Okay, but the concept that usually forces people to pause and rethink their understanding of chemistry is the upper flammable limit.
The UFL throws people for a loop.
This is the counterintuitive part. Above the UFL, the mixture is considered too rich to burn.
Right.
Wait, so if there's too much fuel in the air, it won't burn. It feels inherently wrong to say that an atmosphere saturated with highly explosive gas is somehow safe from ignition. How can there be too much fuel for a fire?
We have to look at the molecules again. Combustion is fundamentally an oxidation reaction. The fuel molecules must violently bond with the oxygen molecules.
Okay.
If the atmosphere is overwhelmingly saturated with fuel vapor, those fuel molecules have physically displaced the oxygen.
Pushed it out of the room.
Basically. So when a spark is introduced, the available oxygen is consumed instantly.
And then what?
The massive surplus of unreacted fuel molecules acts as a heat sink.
Oh.
They absorb the thermal energy of the initial spark, which drops the temperature of the reaction zone below the ignition threshold, and the fire instantly quenches itself. It physically cannot propagate.
It's the chemical equivalent of flooding a car engine.
That's a great analogy.
Yeah, you dump so much gasoline into the cylinder that there simply isn't enough air to let the spark plug do its job.
Exactly.
So fire operates in a strict Goldilocks zone. Not too lean, not too rich, but just the right ratio of fuel to oxygen.
The Goldilocks analogy is perfect for understanding the static chemistry, but in an industrial setting, these concentrations are never static.
They move.
They are dynamic, which creates one of the most lethal traps in the safety profession, particularly involving confined space entry.
Let's hear a scenario.
Consider a massive chemical storage tank that has been drained of its liquid product.
Okay.
The tank is sealed. Inside, the heavy vapors have accumulated to a concentration of 30% by volume. The upper flammable limit for this specific chemical is only 15%.
So the atmosphere inside the tank is double the UFL. It is intensely rich.
Right. So a technician walks up, looks at the external gas monitor, and sees the concentration is far above the upper limit.
They see 30%.
A fundamental misunderstanding of chemistry might lead them to conclude that the tank is inert, that it cannot explode because there isn't enough oxygen.
Because it's too rich.
Exactly. But what happens the microsecond they unbolt and swing open the access hatch to enter the confined space?
The physical equilibrium is broken.
Yep.
You have a dense, highly concentrated vapor inside and ambient air containing 21% oxygen outside. The oxygen-rich air rushes into the tank, and the dense vapor begins to vent out.
And exactly where those two air masses meet, at the boundary layer inside the tank, the 30% concentration begins to dilute.
Oh, man.
It rapidly drops to 25%, 20%, and then it crosses the 15% threshold of the upper flammable limit.
Right into the Goldilocks zone.
In a matter of seconds, the introduction of fresh air has forced that safely oversaturated atmosphere directly back into the highly explosive flammable range. As the technician steps through the hatch, the static friction of their boot scraping the metal grate generates a tiny spark, and the newly diluted atmosphere detonates.
That is just a chilling reality. You can never consider an over-rich environment to be safe because the very act of interacting with it, opening a door, turning on a ventilation fan, even just the natural diffusion of gases stresses over time will inevitably drag that mixture through the explosive danger zone.
You are always moving towards the flammable range.
Yeah. And speaking of sparks, the sources explicitly list common ignition sources. Open flames, space heaters, electrical arcs from non-intrinsically safe equipment, and hot work like cutting or welding.
The usual suspects.
Right. But there is a silent ignition source that requires no spark at all. Autoignition.
Autoignition is arguably the most terrifying physical property on the safety data sheet.
Why is that?
Because it removes the requirement for an active ignition event. The autoignition temperature is the minimum baseline temperature at which a substance will spontaneously burst into flames, driven purely by ambient thermal energy.
No spark.
There is no spark, no arc, no open flame. The environment itself simply becomes too hot for the chemical bonds to maintain their stability.
We have to break down the physics of how that happens. Because every chemical reaction requires a certain amount of activation energy to get started.
Right.
Usually, a spark provides a sudden, localized burst of extreme heat that supplies that activation energy.
Yeah.
But autoignition means the overall temperature of the environment is transferring enough heat into the material to cross that activation threshold globally.
The transfer of heat is the mechanism of failure here.
Walk us through it.
Let's examine a common industrial setup. You have a network of high-pressure steam pipes running through a processing area.
Okay.
Those pipes are radiating intense thermal energy operating at, let's say, 450 degrees Fahrenheit. A maintenance crew is working nearby and temporarily sets a sealed can of industrial solvent on top of the thermal lagging insulating one of the pipes.
Just setting it down for a second.
Right. Now, the solvent has an autoignition temperature of 400 degrees Fahrenheit.
Oof. Even though the pipe is insulated, the lagging is still radiating heat.
It is.
The metal can sits there, acting as a highly efficient thermal conductor, drawing the heat from the surface of the pipe into the liquid solvent inside.
And as the temperature of the liquid rises, its vapor pressure skyrockets. The can begins to bulge.
Fighting the atmosphere.
Exactly. Eventually, the mechanical integrity of the can fails, or a seal gives way, and the pressurized, superheated vapor escapes into the air surrounding the 450-degree pipe.
Oh boy.
Because the ambient environment near the pipe is already 50 degrees above the chemical's autoignition temperature, the vapor molecules absorb the surrounding heat, cross their activation energy threshold simultaneously, and the entire vapor cloud spontaneously erupts into fire.
The heat itself was the ignition source.
Just the heat in the air.
It completely redefines how we must conduct hazard assessments. You can't just look for open flames. You have to look for thermal radiation, conduction through structural steel, and convective heat currents.
You have to map the heat of the entire facility.
Yeah, and it forces us to look beyond the obvious liquids and vapors, which is a perfect transition into the next phase of our analysis.
Right, solids and gases.
Exactly. While liquids command most of our attention, the ASP exam and the realities of a dynamic worksite demand, we understand how other states of matter behave under thermal stress. We need to look at flammable solids and chemicals under pressure.
And the hazard landscape here is vastly more complex than just pooling liquids.
Let's begin with flammable solids.
Okay.
OSHA's definition is highly specific. A flammable solid is a non-explosive material that is liable to cause fire through friction, absorption of moisture, spontaneous chemical change, or retained heat from manufacturing or processing.
There's a lot in that definition.
There is. The concepts of retained heat and spontaneous chemical change really challenge our fundamental understanding of fire.
How so?
Well, we usually think of a fire starting from the outside in, right? A flame is applied to the surface of a solid log, and it burns inward.
Right.
But the OSHA definition describes solids that essentially decide to catch fire from the inside out, based purely on their own physical history and chemical makeup.
It is an insidious process governed by thermodynamics and oxidation kinetics.
Let's go back to the scenario we opened the show with, the palette of synthetic foam.
Right, the midnight shift.
Yeah. Many synthetic materials, resins, and chemically treated organic fibers undergo an exothermic reaction when exposed to oxygen.
They slowly oxidize.
Right. In a single small piece of foam sitting on a desk, this slow oxidation generates a minuscule amount of heat that easily dissipates into the surrounding air. The temperature never rises.
But manufacturing scales up the physical geometry, which changes the thermodynamics entirely.
Exactly the problem. In our scenario, the foam is coming off a heated manufacturing line. It already has retained thermal energy trapped within its molecular structures.
It starts.
Yeah. The workers immediately stack hundreds of these warm blocks onto a pallet and encase the entire cube in layers of tight industrial shrink wrap.
And synthetic foam is an excellent thermal insulator.
It has a very low thermal conductivity, so the heat trapped deep in the center of the pallet physically cannot escape outward through the insulating layers of foam.
It's trapped.
And meanwhile, the slow microscopic oxidation process is still happening, generating new heat.
So the heat of oxidation is added to the retained heat of manufacturing.
Because the heat cannot dissipate, the temperature in the core of the pallet begins to rise.
And as the temperature rises, the rate of the chemical oxidation reaction accelerates.
It is a runaway thermal feedback loop.
The accelerating reaction generates even more heat, which pushes the temperature higher, which speeds up the reaction further.
Hours later, sitting in a dark, quiet warehouse, the core temperature hits the autoignition point of the solid foam.
It begins to undergo pyrolysis, breaking down chemically and smoldering.
The smoldering spreads, eventually breaching the plastic wrap, exposing the superheated core to fresh ambient oxygen.
Resulting in a sudden, violent flashover.
A deep-seated warehouse fire born entirely from the geometry of the packaging and the microscopic chemistry of the solid. It's brilliant and terrifying.
And the regulatory agencies don't just guess at these properties.
No, they mandate rigorous physical testing. The sources cite the testing standard for flammable solids as 16 CFR 1500.44.
The burn test.
Right. To officially classify a solid as flammable, they subject it to a very empirical test. It must ignite readily and burn with a self-sustained flame at a rate greater than 1/10 of an inch per second along its major axis.
It is a literal burn rate test.
How do they do it?
They expose the material to a standardized ignition source and measure the physical velocity of the flame front traveling across the solid.
Yeah.
If the flame propagation exceeds that 0.1 inches per second threshold, it proves the material's internal chemistry supports rapid combustion.
Which earns it the flammable solid classification.
Exactly, and triggering strict storage and handling protocols.
The speed of the flame front is critical, but it pales in comparison to the sheer velocity of our next category. Chemicals under pressure, specifically industrial aerosols.
Oh, aerosols are a whole different beast.
They really are. The globally harmonized system, the GHS, utilizes very rigid mathematical criteria to classify the severity of aerosol hazards.
Right.
It is not just a question of whether the pressurized can will pop if it gets too hot. The GHS classification focuses on the energetic payload the chemical inside will deliver to an existing fire.
Aerosols introduce a terrifying dynamic because they artificially accelerate the phase change of a liquid into a gas.
Okay, let's look at the math.
The GHS defines Category 1 aerosol as the most dangerous classification using two specific metrics. The chemical must contain 85% or more flammable components by mass.
Okay, 85%.
And it must possess a heat of combustion greater than or equal to 20 kilojoules per gram.
That's the threshold.
Yes. Category 2 aerosols encompass the middle ground. Having more than 1% flammables but less than 20 kilojoules per gram, or conversely, having less than 85% flammables but maintaining that high energy output of 20 kilojoules per gram or more.
We need to dissect that term, heat of combustion.
It's important.
This is a fundamental thermodynamic measurement. The formal definition is the amount of thermal energy, measured in calories or kilojoules, evolved or released by the complete stoichiometric combustion of exactly 1 gram of the substance.
A single gram.
Right. It is a measurement of the raw, violent potential energy stored within the chemical bonds of the molecules.
Let's contextualize why heat of combustion is the governing metric for aerosol safety.
Okay, give us a visual.
If a fire breaks out in a warehouse racking system containing standard cardboard boxes, the fire will grow at a predictable rate based on the moderate heat of combustion of the paper and wood.
Normal fire behavior.
Right. But if that fire reaches a pallet of Category 1 aerosols, the physics of the fire change in an instant. The intense external heat from the fire causes the liquid propellant inside the aerosol cans to boil. The vapor pressure inside the cans skyrockets until the structural integrity of the metal fails.
The can ruptures, releasing the pressure.
Yes.
But because the liquid inside is superheated far above its normal boiling point, the sudden drop in pressure causes the liquid to flash boil into a gas instantaneously.
It is a miniature BLEV.
A boiling liquid expanding vapor explosion.
Exactly. The mechanical explosion of the can atomizes the flammable liquid into a massive, highly oxygenated cloud, which immediately ignites.
And this is where the heat of combustion metric becomes horrifyingly real.
Because the GHS Category 1 aerosol packs 20 kilojoules or more of thermal energy into every single gram of liquid.
That fireball releases a colossal, instantaneous wave of radiant thermal energy into the surrounding environment.
It's an energy spike that can completely overwhelm the facility's defenses.
Yeah, the thermal radiation from a rupturing pallet of Category 1 aerosols can instantly flash ignite combustible materials on racks 20 feet away. It generates a heat release rate so intense that it can overpower overhead fire sprinklers, boiling the water droplets into steam before they ever reach the seat of the fire.
The sheer thermal load can weaken structural steel roof trusses in minutes.
The GHS classification recognizes that an aerosol isn't just a container of fuel, it is a thermal weapon waiting to be deployed by an existing fire.
That is the perfect way to phrase it.
We have established a truly daunting inventory of hazards so far.
We really have.
We have flammable liquids sweating heavy and invisible vapors that pool in basements.
Right.
We have combustible liquids waiting for a heat source to weaponize them.
We have solids quietly oxidizing and self-heating inside their packaging.
And we have massive pallets of pressurized aerosols waiting to rupture and release devastating waves of thermal radiation.
A modern industrial facility uses all of these materials simultaneously.
Which begs the question, how does a safety engineer safely arrange this chaotic mix of chemistry inside a single building?
The spatial management of these energetic materials is governed by the principles of chemical compatibility and storage segregation.
You cannot simply build a strong shelf and place everything on it.
Definitely not. An untrained worker's instinct is to organize a chemical storage room alphabetically.
Makes sense to a layman.
Sure. They will place A for acetic acid right next to A for ammonium nitrate, or H for hydrochloric acid next to H for hydrogen peroxide.
Alphabetizing chemicals is a profoundly dangerous administrative failure.
Because you are placing chemicals based on linguistics rather than molecular reactivity.
Right. The sources explicitly demand that incompatible materials must be separated. Mixing incompatibles can generate sudden exothermic heat, release lethal toxic fumes, or trigger massive explosions.
The classic example provided is storing acids and bases together, or mixing waste containing sulfides with acidic solutions.
We have to look at the chemistry of those incompatible reactions to understand the severity.
Okay, let's do the sulfide example.
If an acidic solution inadvertently mixes with a sulfide compound, perhaps a container leaks into a shared secondary containment sump. The resulting chemical reaction rapidly generates hydrogen sulfide gas.
Which is bad news.
Hydrogen sulfide is not only highly flammable, but it is deeply toxic, capable of causing rapid olfactory fatigue and sudden central nervous system collapse at high concentrations.
You have instantly turned a simple storage leak into a lethal atmospheric hazard.
Exactly. And similarly, if a strong acid mixes with a strong base, the resulting neutralization reaction is fiercely exothermic.
It rapidly generates immense heat, instantly boiling the water in the solutions.
Which violently spatters the boiling, corrosive mixture across the room.
And can easily provide the activation energy to ignite nearby flammable vapors.
So the administrative control that prevents this chaos is the Safety Data Sheet, the SDS.
Specifically, Section 10 of the SDS, which covers stability and reactivity.
This section explicitly lists the chemical incompatibilities. The safety professional must meticulously cross-reference Section 10 for every single chemical entering the facility to construct a comprehensive compatibility matrix.
And that compatibility matrix dictates the physical segregation of the facility?
Segregation isn't just leaving a few inches of space on a shelf.
No, true segregation often requires specialized storage lockers with independent ventilation, constructing physical firewall barriers, or even utilizing completely separate detached storage buildings for highly reactive oxidizers.
But I want to focus on a silent, creeping threat mentioned in our sources that frequently defeats even the most meticulously planned segregation matrix.
Corrosion.
Corrosion. It is formally defined as the electrochemical oxidation of metals, the most common example being rust.
It is the process by which a refined metal naturally degrades back into a more stable oxide state.
How does this slow, mundane process defeat our chemical segregation?
Because segregation relies on the physical integrity of the storage infrastructure.
Okay, walk us through a failure scenario.
A facility has flawlessly separated its incompatibles by distance. The highly reactive bases are on the north wall, and the concentrated acids are on the south wall.
It's good on paper.
However, the facility utilized standard carbon steel industrial shelving for the acid storage.
Which seems structurally sound at first glance. Steel is incredibly strong.
Structurally sound, but chemically vulnerable. Over the course of months, microscopic amounts of acidic vapor escape from the containers.
Because they aren't perfectly sealed.
Right. Perhaps the plastic caps are not torqued to absolute perfection, or temperature fluctuations cause the containers to breathe.
Right.
This invisible acidic vapor mixes with the ambient humidity in the air, creating a highly corrosive microatmosphere immediately surrounding the metal shelving.
So the acid and the water vapor form an electrolyte on the surface of the steel, initiating an electrochemical cell.
The iron in the carbon steel begins to undergo rapid electrochemical oxidation. It literally dissolves at a molecular level, flaking away as iron oxide.
The shelving is slowly, silently eaten alive.
The structural integrity of the load-bearing supports is mathematically compromised.
And then,
on a quiet weekend, the weakened steel finally yields to the gravitational load. The rack collapses. Dozens of drums of concentrated acid crash to the concrete floor, rupture, and the massive liquid spill flows across the room.
defeating the distance-based segregation and cascading directly into the containment area of the reactive bases on the north wall.
The resulting exothermic reaction would be devastating, and it was entirely predictable based on chemical incompatibility.
The failure wasn't that the acids and bases were stored too close together. The failure was that the storage infrastructure itself, the steel rack, was incompatible with the chemical properties of the vapors.
This highlights why corrosive materials mandate specialized containment.
Like high-density polyethylene cabinets.
Or metal shelving coated in heavily cross-linked acid-resistant epoxy resins.
You have to engineer the physical environment to withstand the chemical realities of the inventory.
And that requires absolute certainty about what is actually inside every single container.
Which is why strict labeling protocols, utilizing GHS pictograms, standardized signal words like danger or warning, and comprehensive hazard statements are not merely bureaucratic compliance tasks.
They are the only visual indicators an engineer has to ensure the correct material is placed into the correct, chemically compatible infrastructure.
Okay, we have established the complex matrix of where to put these chemicals and who they can safely sit next to.
But the practical reality of a work site is that these liquids cannot stay in their storage rooms forever.
Right. They must be moved, poured, dispensed, and utilized on the floor.
This requires a transition from strategic segregation to tactical hardware.
Let's examine the highly regulated mechanics of safe handling, focusing on specific safety containers, the mathematics of storage cabinets, and the physics of bonding and grounding.
This is an area heavily scrutinized on the ASP exam because it deals directly with quantitative OSHA standards that leave zero room for interpretation.
The regulations recognize that the moment a chemical leaves bulk storage and enters the hands of a worker, the risk profile skyrockets.
To mitigate that risk, OSHA Standard 1926.152 mandates the use of highly specific hardware for the handling of flammable liquids.
The standard dictates that if you are handling more than 1 gallon of a flammable liquid, you must utilize an approved metal safety can.
There are a couple of practical exemptions, though.
Right. Quantities of 1 gallon or less can remain in their original shipping containers.
And highly viscid liquids, like thick roof coatings or heavy adhesives that physically cannot pour through a standard spout, are exempt from the safety can requirement regardless of volume.
But for the vast majority of flammable solvents, the metal safety can is mandatory.
We need to analyze the engineering of that safety can. It is not simply a sturdy metal bucket.
It is an active safety device designed to sever the chain reaction of combustion.
The two critical features mandated by OSHA are a spring closing cover and a flame arrestor.
The spring closing cover is straightforward mechanical engineering. If a worker is carrying a 5-gallon can of acetone across the floor, trips, and drops the can, human reflex might fail, but the mechanical spring will not.
The lid instantly snaps shut.
Right, sealing the container and preventing the 5 gallons of volatile fuel from spreading across the floor and massively expanding its surface area and vapor generation.
So the spring lid mitigates the mechanical spill, but the flame arrestor mitigates the thermal threat.
The flame arrestor is a fascinating application of thermodynamics.
It is typically a densely woven wire mesh screen, often made of stainless steel or brass, inserted deeply into the spout of the can.
Its function seems almost magical until you understand the heat transfer mechanics.
Let's visualize the threat. A worker is pouring solvent from the can into a mixing vat. The lid is open.
Combustible vapors are actively flowing out of the spout, surrounding the stream of liquid.
A nearby grinding operation throws a spark that lands directly in the vapor cloud hovering over the spout. the vapor ignites.
Under normal circumstances, that flame front would instantly follow the vapor trail straight down the spout, enter the headspace of the can where the vapor is perfectly concentrated, and cause a catastrophic internal explosion.
But the flame arrestor interrupts that process.
As the flame attempts to travel down through the spout, it must pass through the tiny apertures of the wire mesh.
The concept of quenching distance is at play here.
Quenching distance.
Precisely the scientific principle. The metal mesh has a very high thermal conductivity and a significant surface area.
So it absorbs heat quickly.
As the intense heat of the flame front contacts the mesh, the metal rapidly absorbs the thermal energy, conducting it away from the flame and dissipating it into the heavier body of the can.
The heat is pulled out of the reaction zone so violently and so quickly that the temperature of the vapor on the inside of the mesh instantaneously drops below its autoignition temperature.
The chemical chain reaction is starved of heat, and the flame is physically quenched before it can reach the bulk liquid inside.
Is an engineered heat sink that physically blocks fire from traveling backward into the fuel source.
It's a brilliant piece of passive safety engineering.
So we have the liquid safely secured in their engineered cans. The next regulatory layer dictates exactly how many of those cans we can keep in a given area.
The indoor storage limits are designed to strictly control the overall fire loading of the building.
OSHA regulations state that you cannot store more than 25 gallons of flammable liquids openly outside of an approved storage cabinet.
If you were just leaving cans sitting on workbenches or tucked in corners, 25 gallons is the absolute legal ceiling for a single fire area.
And if a facility needs more operational fuel than that, they must invest in approved flammable storage cabinets.
But even those engineered cabinets have strict mathematical limits.
The regulations cap the volume at 60 gallons of flammable liquids or 120 gallons of combustible liquids per cabinet.
Furthermore, the standard dictates a mandatory physical clearance of 36 inches between the top of any stored material and the facility's overhead fire sprinklers.
Why these specific rigid numbers?
These limits are entirely driven by the thermodynamic mathematics of the building's fire suppression system.
Okay, break that down for us.
An approved flammable storage cabinet is not fireproof. It is fire resistant.
Important distinction.
It is subjected to a rigorous standardized fire test, such as NFPA 251. The cabinet is engulfed in a roaring external fire, and its double-walled, air-insulated steel construction must maintain an internal temperature below 325 degrees Fahrenheit for a minimum of 10 minutes.
10 minutes is designed to provide a critical window of time for the workers to evacuate and for the overhead sprinkler system to activate and suppress the external fire before the cabinet's internal temperature causes the stored solvents to boil and rupture.
But the engineers must account for the worst-case scenario.
Which is?
The external fire is not controlled, the 10-minute window expires, the internal temperature skyrockets, and the cabinet ultimately fails, releasing its contents into the blaze.
This is why the 60-gallon limit exists.
Exactly. A standard commercial overhead sprinkler system is hydraulically calculated to deliver a very specific density of water measured in gallons per minute per square foot, capable of absorbing a specific heat release rate, or HRR, from a fire.
So the suppression system is a mathematical formula balancing the cooling power of the water against the thermal energy output of the burning fuel.
If the cabinet fails and releases 60 gallons of a highly volatile flammable liquid, the resulting spike in the heat release rate is massive, but it is a known, finite, calculable spike.
The sprinkler system has been designed with enough hydraulic capacity to absorb that specific 60-gallon thermal surge, control the spread, and prevent the structural steel of the building from reaching its critical failure temperature of roughly 1,000 degrees Fahrenheit.
But if a facility manager illegally crams 120 gallons of flammable liquid into a single cabinet and that cabinet fails, the thermal energy released is double what the engineers calculated.
The fire generates more heat than the water can absorb.
The intense thermal radiation overwhelms the sprinkler system, boiling the water droplets into steam before they can penetrate the thermal plume to cool the fuel.
The fire quickly breaches the suppression threshold, spreads to adjacent fire areas, and consumes the entire facility.
The 60-gallon limit is the mathematical linchpin holding the entire suppression strategy together.
And that explains the strict 36-inch clearance rule for the sprinklers, right?
Right. The sprinkler heads utilize specialized deflectors to break the water stream into a highly specific droplet size and distribute it in a carefully calculated geometric umbrella pattern.
If you stack boxes, pallets, or materials up to the ceiling, you physically block the deflector.
You create a dry shadow underneath the blockage where the fire can burn unabated, completely shielded from the cooling water.
It defeats millions of dollars of hydraulic engineering with a single misplaced cardboard box.
The regulations also extend to outdoor storage.
While you have the advantage of infinite ventilation, vertical fire spread remains a critical threat. The sources dictate that outdoor combustibles can be piled no higher than 20 feet, and the driveway separating those piles must be a minimum of 15 feet wide.
The 20-foot height limit prevents the creation of massive vertical columns of thermal radiation that can easily jump gaps to adjacent structures.
While the 15-foot driveways provide the necessary physical access for heavy municipal fire apparatus to maneuver and deploy high-volume deck guns.
We have covered the macro-level storage mathematics, but we must return to the micro-level physics of dispensing these liquids.
We need to explore the absolute necessity of bonding and grounding.
We established earlier that open flames and hot surfaces are ignition sources, but when you are physically transferring a flammable liquid, pouring it from a 55-gallon drum into a 5-gallon safety, can the simple mechanical act of moving the liquid generates its own invisible lethal ignition source?
Static electricity.
The OSHA requirement is unambiguous. When transferring flammable liquids, the dispensing and receiving containers must be electrically interconnected, which is bonding, and connected to the earth, which is grounding.
Most people conceptualize static electricity as a minor nuisance, shuffling across a carpet in socks and shocking your finger on a brass doorknob.
The physics are identical, but in an industrial transfer operation, that tiny shock contains more than enough millijoules of energy to exceed the activation energy of a flammable vapor.
We have to look at the process of triboelectric charging at the molecular level.
When a non-conductive flammable liquid like toluene or heptane flows through a pipe, a hose, or simply pours through the air out of a spout, the physical friction of the liquid molecules rubbing against the solid walls of the container forcefully strips electrons away from their parent atoms.
The mechanical shear force of the fluid dynamics is literally ripping electrical charges apart.
As the liquid flows into the receiving container, it carries that accumulating static charge with it. The liquid itself becomes highly electrified.
Many industrial solvents have incredibly high electrical resistance, meaning they have a very long relaxation time.
They hold on to that electrical charge for a significant duration because the charge cannot easily flow back through the liquid to neutralize itself.
If the receiving container is insulated from the earth, perhaps it is sitting on a wooden pallet, a rubber mat, or even just painted with a thick dielectric coating, the static charge rapidly accumulates on the surface of the container.
The container is acting like a massive capacitor, storing a growing reservoir of electrical energy.
The electrical potential difference, the voltage between the charged receiving container and the dispensing drum, continues to climb.
Eventually, the voltage becomes so extreme that it overwhelms the dielectric breakdown strength of the air separating the two containers. The electrons violently leap across the air gap to equalize the potential.
That leap is the static spark. And the cruel irony of physics is that this spark occurs at the exact location where the concentration of flammable vapors is at its absolute highest.
Right at the spout where the liquid is actively splashing and vaporizing into the air.
You are simultaneously generating the fuel, creating the optimal oxygen mixture, and synthesizing the spark in the exact same physical cubic inch of space.
Bonding and grounding physically neutralize this physics equation.
Bonding involves attaching a braided steel or copper wire equipped with sharp metal-biting clamps between the dispensing drum and the receiving can.
The biting clamps are crucial because they pierce through paint, rust, or grease to make direct metal-to-metal contact, creating a pathway of zero electrical resistance.
With the bonding wire in place, any electrons stripped by the flowing liquid instantly travel through the wire rather than accumulating as a charge differential.
The two containers are held at the exact same equipotential state. If there is no difference in voltage between them, physics dictates that a spark cannot jump.
But bonding alone just equalizes the charge between the two items. They could both still be highly charged relative to the Earth.
Which is why grounding is the mandatory second half of the equation.
Grounding involves taking a second wire from the bonded system and connecting it directly to a verified Earth ground.
This could be a dedicated copper grounding rod driven deeply into the soil, or a designated grounding bus bar integrated into the building's structural steel network.
The ground provides an infinite zero-potential reservoir.
As the flowing liquid generates the static charge, the electrons are instantly and continuously drained away through the grounding wire, dissipating harmlessly into the earth.
The electrical potential never has a chance to build, and the spark is fundamentally prevented from existing.
It is a perfect example of utilizing the immutable laws of physics to defeat a chemical hazard.
We have engineered a profoundly robust defense system. We understand the molecular behavior of the flashpoint. We anticipate the fluid dynamics of heavy vapors. We calculate the thermodynamics of our storage cabinets and sprinkler densities. We harness electrical conductivity to prevent static sparks.
But every single one of these complex engineering controls can be entirely undermined by human behavior.
This brings us to our final operational focus: housekeeping, daily defense, and emergency preparation.
The most sophisticated hazard mitigation architecture in the world will fail if the daily safety culture is broken.
Poor housekeeping is not merely an aesthetic issue, it is a primary driver of industrial catastrophes.
The regulations explicitly mandate that work areas must be kept free of combustible dust and accumulated debris.
The danger of dust is often wildly underestimated by floor workers. They view it as dirt.
But from a chemical perspective, dust is highly concentrated fuel with a massively expanded surface area.
The surface area to volume ratio is the critical factor. A solid block of wood burns slowly because oxygen can only interact with the exterior surface.
But if you pulverize that wood into microscopic dust and suspend it in the air, every single particle is surrounded by oxygen. The reaction rate becomes almost instantaneous.
If poor housekeeping allows combustible dust to accumulate on overhead rafters, ventilation ducts, and light fixtures, you are building a dormant bomb.
And the trigger for that bomb is usually a much smaller, seemingly manageable primary event.
A worker might have a small, localized fire on a workbench, perhaps a rag caught fire. It's a primary fire they could easily extinguish.
But the rapid thermal expansion of air from that small fire creates a pressure wave. That pressure wave travels upward, striking the rafters, and violently lofts months of accumulated dormant combustible dust into the air, creating a massive, highly oxygenated dust cloud spanning the entire ceiling.
The dust pentagon is complete. The dust cloud finds the thermal energy from the primary fire, and the entire ceiling detonates in a secondary deflagration that creates overpressures capable of blowing the concrete walls out of the facility.
Good housekeeping is literally structural preservation.
And that daily vigilance extends to how we handle waste materials, particularly oily rags.
The sources highlight that oily rags and solvent-soaked waste must be kept in fire-resistant, tightly covered containers until they are physically removed from the site.
Let's examine the behavioral trap here. You have a maintenance technician at the end of a grueling 12-hour shift.
They have been wiping down gears with a cotton rag saturated in a flammable solvent or a drying oil like linseed oil.
They are exhausted. They walk past an open plastic trash bin, toss the saturated rag inside, and clock out for the night.
They have unknowingly engineered a spontaneous combustion event.
The chemistry behind the oily rag fire is a classic example of exothermic oxidation combined with thermal insulation.
Many industrial oils, particularly unsaturated drying oils, readily react with ambient oxygen. The chemical double bonds in the oil molecules break and form crosslinks with oxygen, a process that releases a small amount of heat.
If that oil is spread thinly across a metal gear, the heat dissipates into the massive heat sink of the metal and the surrounding air. Nothing happens.
But the technician crumpled the rag and tossed it into a pile in a plastic bin. The cotton fibers of the rag act as a highly efficient thermal insulator.
The oil oxidizes, generating heat. The crumpled cotton prevents the heat from escaping.
The temperature inside the rag begins to climb. As the temperature rises, the kinetic energy of the molecules increases, which accelerates the rate of oxidation.
The faster it oxidizes, the more heat it generates. It is the exact same runaway thermal feedback loop we saw in the palette of synthetic foam.
Except this is happening in a plastic trash bin surrounded by paper waste. The temperature hits the autoignition point of the cotton or the solvent vapor, and the trash can erupts into flames hours after the facility has been locked down.
To disrupt this chemistry, safety protocols mandate the use of specific oily waste cans.
These are heavy metal containers engineered with a self-closing weighted lid that maintains a tight seal.
The can serves two thermodynamic functions. First, the metal body acts as a heat sink, pulling thermal energy away from the rags.
Second, and most importantly, the sealed lid restricts the flow of oxygen.
If the rag begins to undergo rapid oxidation and ignites inside the can, it quickly consumes the small volume of oxygen trapped in the headspace.
Without oxygen to sustain the reaction, the fire literally chokes itself out before it can breach the container.
It requires a culture where workers respect the invisible chemical potential of something as mundane as a dirty rag.
That same cultural respect must apply to the chemicals themselves.
The regulations explicitly forbid the misuse of materials, highlighting that explosive liquids like gasoline must never be used as cleaning agents. You must only use approved high flash point industrial cleaners.
This rule directly combats human convenience superseding chemical safety. Gasoline is a highly effective non-polar solvent. It cuts through heavy machine grease with incredible efficiency.
A worker trying to save time might bypass the approved safety solvent, grab a rag soaked in gasoline, and begin scrubbing a warm machine block.
They are focused entirely on the mechanical task of removing the grease, completely ignoring the kinetic reality that the gasoline, with its negative 45-degree flash point, is rapidly evaporating.
They are surrounding themselves in an invisible, highly concentrated envelope of explosive vapor that is actively sinking and pooling around their boots due to its high vapor density.
The friction of the rag, the residual heat of the machine block, or a static discharge from their clothing provides the activation energy, and the worker's breathing zone becomes the epicenter of a flash fire.
True safety management requires educating the workforce so they understand why the approved solvent, with its chemically engineered high flash point and low vapor pressure, is the only acceptable tool for the job.
And because humans are fallible and entropy is a constant, the final backstop is emergency response preparation.
The sources dictate that employers must provide portable fire extinguishing equipment suitable for the specific hazards present. You cannot just hang a generic fire extinguisher on the wall and consider the job done.
The physical and chemical properties of the fuel dictate the suppression chemistry. If your hazard assessment identifies a storage area for Class B flammable liquids, you must deploy extinguishers utilizing dry chemical agents or carbon dioxide designed to interrupt the chemical chain reaction or displace oxygen.
If a facility machines combustible metals like magnesium or titanium, which are Class D hazards, installing standard ABC dry chemical extinguishers is a critical error.
Because combustible metals burn at such extreme temperatures that they will violently react with the water or chemicals in standard extinguishers, right?
Yes. Applying standard extinguishing agents to a magnesium fire can rapidly accelerate the oxidation, causing the metal to burn with explosive intensity and spray molten slag across the room.
You must provide specialized Class D dry powder extinguishers that utilize graphite or sodium chloride to physically smother the metal and absorb the immense thermal energy.
You must anticipate the specific molecular behavior of the fire before the first spark is ever thrown.
That concept, anticipating the molecular behavior, perfectly summarizes the immense responsibility carried by safety professionals.
Let's take a moment to look back at the massive amount of ground we've covered on today's session of QHSE Talks. We started by dissecting the kinetic molecular theory behind the 100-degree Fahrenheit flash point, establishing the stark dividing line between ambient flammable threats and conditional combustible hazards.
We traced the flow of invisible heavy vapors, analyzing vapor density for ventilation and specific gravity to prevent firefighters from inadvertently spreading burning fuels with water.
We explored the thermodynamic Goldilocks zone of explosive limits, proving that overly rich confined spaces are just a breath of fresh air away from detonation.
We also expanded our view to recognize that heat itself is an ignition source through the mechanics of autoignition, and analyzed how solid materials and pressurized aerosols can spontaneously generate or violently multiply thermal energy in a warehouse fire.
We mapped out the complex chemistry of segregation, highlighting how the silent electrochemical process of corrosion can physically destroy our administrative controls.
And finally, we broke down the engineered physics of flame arrestors, the thermal calculus behind storage cabinet limits, the essential necessity of dissipating static electricity through bonding and grounding, and the daily cultural battle against combustible dust and oxidizing rags.
It is a vast, deeply interconnected web of chemistry and physics. Every regulation is written in response to a physical law.
It is. And before we wrap up, I want to ask you to leave our listener with a final lingering thought. We've spent this entire time meticulously analyzing the hazardous chemicals we intentionally purchase, bring into our facilities, and store in specialized cabinets.
But looking beyond the inventory manifest, What is one overarching, perhaps unsettling concept the safety professional should take away from all of this thermodynamics and chemistry?
We dedicate massive resources to policing the chemicals we introduce to the environment. We check the vapor pressures, we run the grounding wires, we monitor the LEL. But consider the physical environment itself, the building you are standing in.
What if the very materials constructing your workplace, the structural steel hidden behind the drywall, the concealed polyurethane insulation in the walls, the microscopic layers of dust slowly, inevitably accumulating in the dark spaces above the drop ceilings, are silently reacting right now?
Oxygen is an incredibly aggressive, highly reactive chemical, and we are completely submerged in it. Everything around you is slowly oxidizing. The metal is trying to rust, the polymers are trying to degrade, the dust is waiting for a pressure wave.
Fire isn't just an unfortunate accident. In a highly oxygenated atmosphere, rapid combustion is a natural chemical state, waiting for the exact right excuse to accelerate. Are you, through a misunderstood vapor density, a missed grounding wire, or lax enforcement of housekeeping, providing the environment with that excuse?
That completely changes the paradigm. It forces you to look at the entire physical structure not as a safe haven, but as a complex chemical system waiting for a catalyst.
Thank you for framing it that way, and thank you, the listener, for committing to this incredibly dense technical journey with us today. Remember, mastering AST exam domain 4. Topic 2 isn't about checking a box for a certification. It is about fundamentally rewiring how you view the world, equipping yourself with the scientific knowledge to look at a seemingly quiet worksite and see the invisible kinetic hazards before they find their excuse to ignite.
Stay curious, stay vigilant, and apply this deep chemical understanding directly to your next hazard assessment.
We will see you on the next edition of QHSE Talks.